The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI Conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content. You can earn continuing education credits through ACI's online CEU program. Visit www.concrete.org to register. ACI Conventions provide an opportunity for networking and for keeping up to date with the latest in concrete technology and practices.
Our first presentation is Cost-Effective Energy Efficient School Design by Dr. Mark McGinley, Department of Civil and Environmental Engineering at the University of Louisville.
Thank you. Thanks, Steve. All right. Thank you very much, everyone. You might wonder what a poor structural engineer is doing talking about energy efficiency. I, for a number of years, was in the architectural engineering department down in North Carolina. Got forced to look at energy efficiency for a number of years, and it kind of stuck. I've been playing around in this area for a little while, as well as in the structural area. What we were asked to do in Kentucky is we were approached and asked the question, how do we go about and do cost-effective energy efficient design for schools? There were a group of architects and designers in that particular area that were really pushing zero energy. The state funds centrally a lot of the schools in Kentucky, and they were finding a huge increase in price per square foot in the buildings, particularly as more and more architects and other designers adopted LEED. And so they wanted to know, they wanted to support this, but they wanted to know if I have a limited amount of funds, where to put that dollar. Where would I get the best bang for the buck if I was investing in energy efficiency in this building system? Where would I put it first? I'd like to acknowledge, first of all, the work of 2 mechanical engineering students that I had, graduate students I had working on this project, and Mr. Kevin Muldoon and Mr. Chad Riggs. Their effort in this was very extensive. The funding for this particular effort was provided by the Kentucky Renewable Energy Consortium. Now, what did this study do? What we were looking at is focusing on conventional construction. We looked at how the schools were actually being designed and built. We looked only at the range of climates initially that were present in the state of Kentucky. And then what we did was looked at how the building performed analytically, and then looked at that energy performance and also cost performance on the schools, on looking at how to develop a holistic approach to which one is the most cost-effective to use, which one, again, gave us our best bang for the buck. Here's the school system that we looked at. This particular building is a prototype building. We actually had proposed originally to look at a typical elementary school, a typical middle school, and a typical high school. Unfortunately, like most government programs, it was reduced. What can you do for half the amount of money? Actually, it was a third of the amount of money we had originally proposed. And so we focused on a middle school. We were looking for a typical design that would represent kind of the state of the art of the designs out there. There are a number of different websites, just for your information, out there that go through and look at what they call model or prototype designs for school system. This one came from the School Clearinghouse organization, and it is a design from there. We took that, modified it a little bit, and used that as our prototype building. If you'll note in here, we chose this. It was about 160,000 square foot. It had a two-story classroom section in here, and it also had a gymnasium, an auditorium, and a kitchen with a cafeteria attached to it. So it represented not only a single-story elementary school, but it had a lot of the aspects that you would get also in a high school, typical high school design. Our base design for the school looked at a cavity wall system, a masonry cavity wall, and it was designed to meet the prescriptive requirements that are described in the ASHRAE 90.1 standard, as a number of the speakers ably talked about earlier today. We went through a base design in here, setting up in there just using these prescriptive requirements for the fenestrations, the R values on the roof. In this case, for our climate zone was an R22. Approximate R values for the walls were around 9.5, 9.8. And we set this basic building up. We went in and we used the eQuest analysis program, which is a holistic energy analysis program that uses the DO2 energy analysis engine. And I won't go into a discussion of that because the previous speakers talked a lot about those particular programs quite ably. We looked at 5 different Kentucky cities: Corbin, Covington, Louisville, Lexington, and Paducah. And you can see the basic visual from the model. Nice thing about eQuest, it has a really nice front end and really nice back end, so you can create some nice graphics and validate your zonal models, etc. What we did then is came out and took at the annual energy use, if you'll see down in here, for each of the different cities, using Louisville down in here for both electrical energy use, and in our base system we used a boiler system for heating and a chiller basic DX unit for the cooling on the system. We used standardized schedules for the classroom space occupancy, etc. in that run, and we got the annual energy use, both electrical energy and heating gas energy, converted that to an overall energy use per year, and then we converted that to a energy use index, in this case which is 132 for the base building, compared that to DOE averages. It was a little bit on the high side, but we were fairly comfortable with that. And it's consistent with some data. We have a center at the university that goes out and does, as a state mandate, energy audits for school systems, the KEEPS Center, and it seemed very consistent with the data that they were actually seeing on some of their schools that were in actual operations. It was within the range they were measuring. Based on that, we then said, okay, let's go out there and see what kind of options that we would have available to us, what are designers using out there. We sent a set of surveys out to the design community. We actually talked to them. I did a number of seminars to the AIA conventions locally, went and saw a number of design offices, talked to facility managers, contractors, reviewed a bunch of guidelines, both promulgated by the Department of Energy, NREL Labs, and others on how to design energy efficient schools. And we identified a series of mature alternative energy conservation measures, or ECMs, that would be typically at least considered for school designs in the Kentucky area. We then individually incorporated each of these ECMs into the building model and ran an energy analysis over a year's period of time for all 5 of the Kentucky cities. Some of the things that we looked at more efficient lights, going to T8 lights and high output T8 lights instead of the standard T12, and in some cases in the high bay areas, the halides. We looked at more efficient HVAC systems, both conventional systems and non-conventional system heat pumps. Ground source heat pumps are in vogue right now in our area for use for cooling and heating and system in high energy efficiency designs. Looking at daylighting controls, setbacks on those controls, energy recovery, ventilation systems, variable frequency drives on a variety of the different motors in the HVAC systems, both ground source and water source heat pumps, enhanced building envelopes, and we went through a wide gamut of different types of exterior wall systems and roofing systems, both light and light gauge steel systems for the walls, as well as the roofing systems. And also we had heavy thermal mass where we went and used ICF systems in addition to our traditional cavity wall with varying degrees of R values for the insulation in the cavity. We also looked at tighter envelopes. We went to the minimum requirement by the ASHRAE 90.1 for air barriers, and then we went up and down off of that range to try and look at the effects of either a leaky envelope and a tighter envelope to see how much of an effect that would have on the overall energy use. We looked at occupancy sensors, variations in the control strategies and schedules based on occupancy, etc. So we looked at all of these things, and we looked at each one of them and their effects on the performance of the building in annual energy, as well as we looked at the combined effects, because you can't simply add those individual effects all the time. You get some trade-offs, and I'll talk a little bit more about that in a minute. Okay, so we went through and ran a bunch of these things. If you take a look up in here, let me get this going in here. You can look, I've expanded this out in here, and you could look at going with ICF walls versus our standard cavity wall. We get about a R increase of about 10 for the difference in the walls, but we only get about less than 1% reduction in overall energy use within the building. Similarly, we looked at lighting. We got a significant reduction in the energy, as you can see up here, the electrical energy use, comparing it to the electrical energy use in the base line down here. But we overall only got a small change in overall energy use, and I'll talk about why that is so in a few minutes. Looked at modifying schedule, okay, using occupancy sensors to modify when the lights come off and on. Again, we got a reasonable reduction, or a small reduction, on the energy use for that. Where we got the huge or larger reductions in here is modifying the fan schedules. For instance, if we shut down the HVAC systems during the unoccupied periods in the school system, that's really easy to, or school building, that's easy to identify, 7 p.m. to 6 a.m. And then simply running the HVAC system when we have that set point hit a temperature that would require heating or cooling. And we were able to get a 21% reduction in overall energy use by that building using that. In general, I'm going to go through a summary right now of the energy use reductions that we get. If you looked at the reduction or the change out in the lights, what was interesting is we got a 6% reduction in the energy that was used for the lights, but the heating energy went up. Okay, the waste heat that's produced by the less efficient lights actually were reducing our heating loads. The EUI, the energy use index, remained almost unchanged during that. We did, however, because the electrical energy was costing us more, even in the state of Kentucky, which I believe still has the third lowest electrical energy rate in the country, our cost savings was still around 3%, so it was reasonably good. The envelope improvements that we did incrementally did not have a huge effect. Generally, individually, they had less than 1% of an effect, with the exception of Lexington, its climate was such that some of the envelope improvements had a higher effect than that. And in deference to the previous speaker immediately in the first afternoon session, that's based on analytical performance, not on actual performance. We also got a significant increase by what I would call a fairly minor increase in the boiler efficiency, and not a very high cost one. We were able to get about 9% reduction in energy by increasing the boiler efficiency to 90%. We were kind of surprised by the results that suggested that the energy recovery ventilation systems that we looked at actually in some cases increased the overall energy use by the building. Tracing back down to try and understand that, it looked like the mechanical ventilation that we require by making it airtight and then requiring these energy recovery ventilation systems, the additional fan energy on that was more than compensated for the actual energy recovery. We went into the literature and found that others had found similar results both for actual analytical work and test data. The Florida Solar Energy Center had taken a look at a number of facilities and found similar results in certain conditions there as well. Controls seem to be where you get the greatest effect. Setbacks, modified fan schedules, looking at minimum airflow reduction using your VAV system, and I'll talk about each one of these in subsequent slides. But when we looked at the combined effect, we looked at some of the most effective energy efficient measures. We combined them together using a conventional VAV system with a chiller and a boiler. We were still able to get a 56% reduction in the energy use in the building with very, very little increase in costs, and we'll talk about that in a minute. We were also, once we took a step up into geothermal systems, we get the huge reduction, as was pointed out in the previous speaker. Selection of your HVAC system has a huge effect on the performance in the building. Here's what I'm referring to on the setbacks. We looked at three different conditions. One was in occupied. We were at a banding around 2 degrees. When we were unoccupied, we were looking at just a 16-degree setback, where we were looking at 64 to 80 degree Fahrenheit, and then we used a very aggressive setback and went to 55 degrees and 90 degrees on those. And we were able to get a significant reduction in the energy in the building just by very simple setback controls on that building. Now, all you would need is a programmable thermostat, or if you had a DDC system, automated system for the building. It's not that hard to incorporate that. We actually looked at the costs of that, which I'll talk about in a little bit further down. One of the things that you have to look at, though, is when you allow too high of a setback, the same thing you run into when you do nighttime ventilation. Humidity control is very, very important. If you don't control humidity, you can have some real problems with indoor air quality, and in particular mold and mildew that are generated within the building. So you have to be very, very careful that you understand the climate that you're designing for when you set these setbacks. The VAV minimum airflow, we could get up to a 25% reduction in energy use on that. And what that did was allow the damper controlling the minimum airflow to fully close. Typically, they're not designed to fully close, so that they get a minimum amount of air exchanges going into each of the spaces, which is required by code, but because they assume all spaces are occupied. And so that's a typical design practice, at least in the areas that we investigated. If we use an occupancy sensor to control that, so if no one's in the space, you don't need any airflow, we can save a lot of money. A lot of energy, rather. Modified fan schedule, again, periodic ventilation, where we shut the entire system down unless it needs to mitigate temperatures, and then it would only cycle on for an hour. to better understand all of the results we got, what we did was go through and took a look at, okay, how could we present this data so it was meaningful, particularly to our focus group was to try and educate designers on what are the best energy conservation measures, or at least the ones that they should look at first. So what we did was take a look in here, and if you look on the, here we go. If you look on the right-hand side here, on the right margin of that graph, you can see the cities here. The vertical axis is percent energy reduction, or actually reduction in energy use index in this case. And then you have a variety of different energy conservation measures on the left. The C measures here, C14, C3, etc., are improvements in the envelope of the building, whether it be increasing the R value in the insulation in the walls or in the roof, etc., or in the air barrier, making it more airtight from the code minimum. You find that they have very, very little effect, small bars that go up. Where we get the larger and larger effects are all in the mechanical area. These are the M's. Or in the combined ones where we're going into the G options, which incorporate up to an 80% reduction when we start to get into the geothermal heat pump systems, particularly when the ground coupled. That's when you're getting the very, very high reductions in your energy use. We said, okay, that's fine, that's energy. Well, how much does each one of these ECMs cost us? We said, okay, how do we get a basic cost in there? So the first thing we had to do is look at our typical costs of energy in our local area, and we used typical LG&E and KU, which is Kentucky Utilities, rate structure to go in and estimate for each kilowatt hour or BTU that we provide how much is that costing us. We then did a estimate on the building. We used a means analysis and then had all of our figures reviewed by a certified construction estimator. And our building was around about $17.5 million, which is about $111 per square foot. Not a high level, that's for the base building. It wasn't very costly. They were going up to about $175 per square foot, and that was beyond what they were comfortable funding, because they had been typically funding about $125 per square foot up until this big push for energy efficiency. So we felt we had a reasonable value for that. We conducted quantity takeoffs and estimates from feedback, both using the means catalog, going through a certified construction estimator, and input from contractors and others who have done actual work in energy efficiency. Both of the students I had working for me were working for a consulting firm whose prime practice was doing energy efficiency analysis and retrofitting of existing buildings at the time, so they had a lot of input they could bring into this analysis. We looked at, first of all, simple payback, taking the energy costs that we saved, the yearly energy savings, compared that against the actual cost of the ECM, and we calculated a simple payback. We also looked at around 4.5% interest rate and about a 1.5% estimated increase in energy costs. We probably should have, in hindsight, reversed that. But it was an overall increase in cost of around 6% per year, which we thought was quite aggressive. And what we did was looked at what was the first year where the ECM would be self-funding, where you get a net return on your investment. Okay, what you can see in here is the costs in here. I just want to point out very quickly is some of the savings in here. Some of the savings that we had, simple payback, it cost us nothing. For instance, orienting the building at different orientations, and we did it at 15 degrees. and I've just showed some of them here in this table. And we just cranked the building around. We assumed that was going to be a no-cost ECM, and in some cases we saved up to about $100 or close to $100 per year in energy, no-cost ECM. In some cases we got the basic cost, for instance, of increasing the insulation on the roof. It cost me about $85,000 to do so. The savings per year is about $330, and so we're looking at 255 years for a payback on that. After we looked at beyond 300 years for self-funding, we put a dash in there. So with the cost of interest for that, for the dollar value on that, we couldn't actually get it to pay within 300 years. We gave up. Because I don't know about you, but convincing any owner that 300 years is a viable return, I don't think so. So, not in our culture. One of the things that was interesting here was this analysis here is there seemed to be, at least in Kentucky, this thought that if a little bit of insulation is good, a whole lot more is better. It's the sort of inertia in the U.S. where bigger and better is better, and bigger and more is better. It is true that adding insulation reduces energy use. But if you look at the energy up here, these are the savings on a yearly basis. These are the R values. If you double the R value, and in this case it's the CMU wall, you'll see first there's a tail off after a certain point. And that tail off has been documented. It's been confirmed by a lot of tests and analysis done by Oak Ridge National Labs and others. And in fact, some of the first work that was done in ICF systems recognized this particular tail off. It does not even recognize, this was for a fixed amount of about 28% fenestrations for that building. It's around that. It does vary a little bit. That was the average on the wall on a per wall basis. There were some clerestories within the building because we wanted to look at that effect, because most buildings, at least the newer buildings being designed in the Kentucky area, had clerestories. You can see the roof always gives you a reasonable, you go up, it goes up in a fairly uniform manner, but again, the return is not very high. And so after a certain point, you will always get energy savings putting more insulation in the building, but how much are you getting for the input in there? Maybe you want to look at something else. Similarly, we got a paybacks for, and I just want to point a couple of these things out. I wasn't sure of this modified, for instance, using variable frequency rods, which is growing in interest in here. If you look at here, paybacks less than 2 years. All of these ones where I'm getting paybacks of less than 2 years are of interest to me because they are something that I can very easily incorporate in there, convince an owner that they're important, and then I can confirm with actual performance. This is what my model suggests to me. We can at least guide the designers to look at these sorts of things first. Lower the payback, the more likely I'm going to get a return on my investment. As I said earlier, the more efficient lights and occupancy sensors on the lights have a lower payback periods in new schools. Although aggressive sensor-driven daylighting, if you look down in here, may take a while. All right, so going in and doing daylighting just to get energy efficiency out of that, it's going to take a little bit longer to pay that back, around 17 years, because of the additional controls that are necessary, but they do pay back, and they have other benefits. If you look at all of the studies that relate to daylighting in the performance of the students with higher levels of daylighting in there. So I just wanted to point out or highlight the fact that energy efficiency and economics aren't the only design criteria that we have to look at here. indoor environmental quality, of which quality of lighting is one aspect we have to be aware of. We did a similar analysis, again, to present this graphically, and you will see what we're looking for is shorter bars this time. The large bars represent longer payback periods, and you can see that they do vary with climate, even within the subclimate we're dealing with in a climate zone 4, by the way, in the reduced ASHRAE numbers, or climate zone numbers. We were getting very, very low paybacks in the mechanical area, paybacks, where we combined the VAV all, okay, when we looked at that entirety of that, we got almost 60% reduction in energy, and our goal with our mandate by our state governor was 25% reduction. We were more than meeting that with paybacks well below 2 years. So even with conventional systems, if we think through and think about how that building is supposed to perform, we can go a long way in reducing the amount of energy that's used within the building. Interesting to note, these geothermal heat pumps, 80% energy reductions, but typically your paybacks are in the 20 years plus. The installation of the ground loops are very expensive, particularly in our area, which we had to blast in most of the areas in Kentucky because of the limestone. Okay. We then said, okay, well, that was very interesting. We said that the envelope had less of an effect. We finished our study and published that and gave that to the Kentucky state government. Then we asked the question, well, is this typical for other climates? So we reran that base school in using some of the critical ECMs that we looked at in 3 other, using weather data for 3 other locations, Dallas, Miami, and Madison, Wisconsin. And here's what we found. We found typically a similar result. Okay, Covington is one of the cities, Covington and Paducah, defined the range of performance for climates within Kentucky. We found that in the Dallas area, it's appropriate for here. We found similar results from that, although in some cases envelope improvements actually reduced the performance of the building, i.e. increased the energy. In Miami, we got a huge decrease in performance in the building, increase in energy use by putting more insulation within the envelope. Kind of counterintuitive, but that has been found by many others and published, and it's actually been confirmed by tests. We get a similar result, though, when we're looking at the mechanical behavior of the building systems. So controls have a greater effect on the performance. Controls, HVAC systems, how we run that building has the greatest control on how much energy is used within that building. And what was true in Kentucky is generally true throughout the range of climates in the U.S. All right, and this is just a different way of looking at that. Which control options, whether a ground source heat pump has a greater effect, you can see that where we're cooling, the ground source heat pump has a greater effect than when we're heating. That's just one of the aspects that you look at, but it still has a very high effect. All right, in conclusion, or in summary, we were able to save over 50% using typical school designs, okay, and conventional HVAC systems. All we changed is our control strategies. These improvements generally had paybacks well below 3 years. The use of ground source heat pumps greatly increased the energy saved, but our paybacks were generally above 20 years. Envelope improvements had, for our configuration of school, had little effect on the overall energy used, at least for the climates that we investigated and with the limitations of the accuracy of our model. Generally, they had very long payback periods, in excess of 100 years. Many of the findings that we've had for this particular study can also be used when we're investigating retrofit strategies, particularly for buildings that were built in the 70s and 80s, because most of them used the very, very common configuration, used this masonry cavity wall system. And so a lot of what we found from this investigation is also being used to inform some of the decisions from various school districts in Kentucky on retrofit strategies as well. We are also happy to see that most of our findings seem to be applicable not only in the climates that we looked at, climate zone 4 in Kentucky, but also applicable to other climates as well. I think I finished up reasonably closely to time, and I want to thank you for your attention and invite any questions you might have.
I wanted to ask you if you could possibly make these studies available and what the cost will be, and also can you run a custom simulation for, say, Austin or San Antonio or whatever city someone else would like?
Yes to all of those. Okay. We'll talk outside about the rest of the question. Yes. Yes.
Two questions here. You might have said this and I didn't hear it, but was the heating system natural gas and cooling system like?
It was a boiler system that was gas-fired, and for the heating system, and it was a DX chiller system, so it was electrically driven.
And did the government give you a threshold payback that will be required in the state?
No.
So you went at it
Completely open. What we try to do is find out from the local design community is what they were using and what they were looking at to try and make this as applicable to them as we could, to make this document as useful as the state-of-the-art in the area it was intended to be applied. Yes, sir.
Does COVID play any role in your computations and how we?
Yeah, the DOT analysis that we use, the eQuest analysis, does account for the thermal effects, the mass effects there. We used mass walls and light walls in there, so yes, it was incorporated. We used ICF wall models as well that have been calibrated through the DOT work at the Oak Ridge National Labs. All right, I thank you very much for your attention, and please listen to the next speaker. Thank you.